the webinar. My name is Linda Capodici. I am from HANZA Engineering. Thank you so much everyone for taking the time to join this webinar with the complex subject troubleshooting packed bed and internals columns where they are not working according to design. We will record the webinar and we will distribute the recording after the webinar. After the presentation, there will be time for questions. And of course, you're more than welcome with questions also after the webinar, if there will be any. Now I will leave the word to Mr. Edward Verbund from RVT Process Equipment, that is the Business Development Manager. Edward, over to you.
Yes, thank you very much, Linda, for the introduction. And welcome to all of you from Germany to this RVT webinar today. It's good to see that we have a very interesting group today with a lot of engineering experience, and that means very valuable discussion partners for RVT. And we have put together an interesting presentation for you, as Linda mentioned, with an item that many of you have certainly come across, namely problems that may occur in packed bed scrubbers. But of course, we will not only show you the problems, but even more important, we also show you the solutions we have as RVT. It is therefore with the greatest pleasure that I want to introduce my colleagues to you, Dr. José Luis Sola and Mr. Uwe Franz. They have prepared this presentation today and both have a lot of experience. Where José works more on the, let's say, on the process side, and is the specialism of Uwe more on the mechanical side. And that means for the topic today, a great combination. And we are looking forward to a fruitful webinar and at the end, your questions and your feedback. Well, before I hand over to Uwe and José, I want to thank HANZA for the organization of today's webinar. So, Linda, thank you very much for it.
Thank you.
And well, that means now, José and Uwe, the floor is yours. Go ahead.
Thank you, Edward and Linda, for the very kind introduction. It's a pleasure for us to be here and to share our knowledge on troubleshooting with you, or some examples that we have worked with in the last years. My name is José Sola, and sitting next to me is Mr. Uwe Franz. And good morning. And I will start the presentation. I will present about 3/4 of it. Uwe has been dealing with some of the troubleshooting problems that we have in our presentation, and he will also take part presenting some of them. So I will share my screen now. I hope everybody can see the title slide.
Yes.
Okay, so I will proceed I will start with the presentation. So the presentation that we are having today deals on troubleshooting. As you know, troubleshooting is not easy to define, but one can say that we speak about troubleshooting when a column is not working as designed for whatever reason. It's a very complex topic, since, as you know, we have not only the column and its internal packings, we also have periphery, piping, pumps, etc. Obviously, as mass transfer equipment manufacturers, we mainly deal on troubleshooting that regards mass transfer equipment and also their boundary internals, liquid distributors, gas inlet systems, liquid inlet systems, droplet separators, and so on. So how is the procedure for RVT to deal with troubleshooting? As you can see here, obviously we request from our customer all necessary data and informations that he has on column. It might be pressure drop before the problem, during the problem, after the problem, or the challenge that he's facing in the column. We need to validate every single design of the internals and packings or trays that are inside the column. We need to check their drawings as well. Eventually, if needed, we do offer the customer the possibility to go on site and have a look on the parts, on the internals, on the packing, and evaluate better, or be able to make a better evaluation of what is going on. And what comes out at the end is that we develop solutions that solve the troubleshooting problem. So in this presentation, we will start talking about a troubleshooting problem, which is commonly occurring for many customers or some customers with which we deal with, and it is troubleshooting related to fouling. And then we will present 3 case studies dealing with troubleshooting on different internal parts: liquid distributor, a gas distributor, and a droplet separator. So I will start with the topic troubleshooting related to fouling. As you know, if we are talking about fouling, we can identify regarding internals inside the column, packings, etc. We can identify typical problem zones. There are more sensitive zones to fouling, and those are liquid distributors, collectors, droplet separators, and obviously also the column sump. Packing can be seen as less critical, but only if we are talking about random packings and with a considerable size. This would be somewhere above 50 millimeters. And in combination with rather high liquid loads. If we have a very low liquid load, the fouling has easier to accumulate at some parts, etc. Structure packings are another story. So structure packings, as you know, they have a completely different geometry. They are constructed with plates, with very narrow channels. And the liquid can and the gas can mainly move between the plates and not across the plates. So that means that the sensitivity to fouling is in random packing less critical than for structured packing. What I still I still keep on talking about packings. The typical fouling, how a customer can identify packing fouling is that you observe a steady increase in the pressure drop inside your column. So after start running a brand new column with brand new packings, you will probably, or the column will deliver the pressure drop that we calculated according to the specified process conditions. And if after some time, 6 months, 1 year, whatever, the pressure drop starts to slightly increase, and this increase keeps going throughout the time, this is a symptom for packing fouling inside the column, and this will end at a certain fouling level. As you know, the packing will block in an amount that the gas velocity locally doesn't allow the liquid to flow down the column, and so we reach the so-called flooding of the packing. So this would be the end of a stable column operation, and at that point is no return. You need to open the column, you need to clean the packing or replace the packing. Now I will continue. We obviously have designs that are optimized to deal with solid contents and to avoid stagnant zones causing settling of solids, to avoid dried spots. But nevertheless, the customers have contacted us in the past, and every year with some pictures with blocked distributors after they saw a malfunctioning of the column regarding its performance. So we see here a truss distributor made of plastic. And you can see that the troughs are almost completely, some of them filled with mud. And then we are asked, how could we optimize the geometry, the design of such internals, so that they do not have so much maintenance work to do, and especially not in so short period of times. And the solutions, the developed solutions that we have delivered to our customers dealing with the very dirty fouling applications, I would like to show you in the next slides. Here you can see a special truss distributor design where we have used obviously big ground holes, as big as possible in the truss themselves. But we have here a special feature. You see here the main feed pipe and the secondary feed pipe feeding the individual truss. But you can see here a smaller pipe. This smaller pipe is now also delivering the liquid additionally at the end of the truss. At both ends of the truss, here we would have the symmetry, another pipe and another flushing. So here, the stagnant zone where the liquid is calm and the mud would accumulate is pushed, is flushed, is in movement, is put into movement, forced to move, also at these critical slow motion areas, so that we avoid the stagnant zones at the solids keep suspended, so that they do not accumulate in the truss, and they don't cause this massive blocking of mud inside the truss and malfunctioning of the liquid distributor and maintenance problems. Another possibility that we have developed for a customer was to combine the truss, so we don't have individual truss with the stagnant zones at both ends. Now we have a pair of truss that have been combined, so that the liquid can steadily move continuously. And how we achieve this movement, here you see a parting box feeding the truss, and the parting box has been foreseen with these bending or plates, bended S-shaped plates, so that the liquid becomes a momentum velocity on one direction, so that again solids are suspended and the mud leaves the truss and does not accumulate. We have done this for a fertilizer plant. As you can see here, the drawing, it's a huge column with support beams, and here you see the truss inside the column, 7.6 meters in diameter. Another solution that we developed for another customer was, in this case, he had really big problems with the mud, and these solutions, even if we presented them, he wanted something even better, that he can really be sure that the mud will, even if it was moving on the other case, that the mud is not going to accumulate. So what we did, we have used not a flat truss floor, but we have used an inclinated floor. And at the end of the truss, here and here, there is at the bottom an opening. You will see it here. That is the built liquid distributor, truss distributor. As I said, now the truss are not connected, but they have the bended floor. You can see here the middle section. This is exactly the middle, and then it goes down to the side here and here, and the very end is open. So now we don't create that movement, but by doing these very big holes, we can be sure, and the slope, we can be sure that the mud is going to easily leave the liquid distributor and not accumulate there. And finally, I think for the same customer, what we did, he wanted to, or another customer probably. So here, what we did is a solution that he can flush the trough and free it from any solids during maintenance work. You can remove this end plate. This end plate at both ends can be removed when the maintenance works have to be done, and then liquid can be flushed inside the trough, and everything which might have accumulated will be very easily cleaned. And the most important thing, as you can see here, there's no need of dismantling this liquid distributor. So during the maintenance work, you can easily remove the plate, put your flushing tube pipe here in the middle, and easily remove all dirt from the trough. The next example that I want to share with you is how we offered a solution for a customer. He had having problems with a liquid collecting tray element. You can see how the collecting tray looked like. It was almost completely blocked. This customer had already bought this combi element or collecting tray element from 2 different manufacturers, and with none of them he could run more than a couple of months the plant before completely fouling of the collecting tray occurred. And they contacted us in order to discuss this and to find a solution that is not state of the art, because we also had obviously similar constructions, but we developed a solution for him. We presented that, and I want to show what we came up with. So you see here what we call liquid collecting combi element. Combi element because it has 2 functions. On the one side, it supports the packing. It works as a packing support, but also as a collecting device for the liquid. And this part, we have removed the collecting vanes, delivering the liquid to the individual troughs so that you can see what is below. So you see this kind of grid. This is obviously there so that the packing doesn't enter the trough and block the ground holes, etc. We need to foresee this. But what we have done with this design, the disadvantage of this design, this is the state-of-the-art combi element design. We have here risk zones for fouling, for solid accumulation. This is the clogging at this inlet grid where the rings will be also obviously be there. And on the other side, we have these stagnant zones at the end of the troughs where mud can accumulate. And this is the solution that we developed. And now you can see the troughs are here, the dark parts, and in between here we have now the path for the gas, but we have some additional element. We have these pipes, and these pipes end with several nozzles feeding along this grid. The grid here is again the grid on the next vein. The grid you must imagine it here. So now this row from this row of nozzles, the grid can be flushed whenever the customer wants. This can be also during operation, and he can flush and clean this part in order to remove any accumulated debris, dirt, fouling. And an additional feature for the same liquid collecting combi device that we developed for him, we also used the sloped the sloped floor of the trough, but also with an integrated flushing and developed flushing system. So you see here the blue line is the floor of the trough, and we have a second chamber just below the floor where the liquid coming from a piping system is going to be forced to flush out through openings at this sloped floor, so that the liquid is going not only to move because of the slope, but also to be forced by the flushing liquid to leave the trough and not accumulate at all. And what we can see, is that the customer was very happy with this solution. The solution worked perfectly, worked excellently, and he can run now the column steadily without fouling problems. So it is a very good story to tell. The next example that I would like to share with you has to do with troubleshooting on a liquid distributor, not dealing with fouling, obviously. So in this case, we were dealing with a flue gas scrubber in an incineration plant where heat was recovered by cooling condensation. And the problem that was that the customer was having is that, or facing, is that the heat recovery that the column was designed for couldn't be reached. So he opened the column and installed temperature devices, 16 temperature devices distributed across the column section. You see here an Excel, a cut of an Excel sheet, just with the numbering of the 16, the position of the 16 temperature thermo devices, and here you can see which temperatures were measured by these 16, the position of these 16 thermo devices in the column. Blue means obviously colder, hot, red is hotter, and the colder, the darker blue, and the hotter, the darker red. So we can easily see there was obviously a much difference in the temperatures if the temperature devices were placed at this side rather than at this side, as you can see here. So we were asked what is happening here in this column. We looked at we then looked at all the documentation that we have regarding the column. The column is a big column, above 4 meters in diameter. It has 3 packed bed sections, a quench section below. Then we have a first condensing section where the gas is cooled down to about 40 degrees, and then we have a second bed above it to further cool down and recover further energy. And the first important thing that we wanted to know where these temperatures had been acquired, and so we could. The customer told us they measured them here above the bed number 2. So having said that, we couldn't obviously yet know what was happening, because we didn't know, we didn't have any temperature profile here, so that we can maybe identify if something is coming from here and is going also up and affecting what happens here, or so this was an open question yet. But what we needed to analyze obviously is our design of the liquid distributor. How have both liquid distributors here and here been designed? Is there any error? And so first we looked into the liquid distributor, which was just below the section where the temperatures were taken. So you see here the drawing of that liquid distributor. The liquid distributor is a truss type liquid distributor with single troughs, not connected. Yes, we were not dealing with fouling here or whatever. How the liquid is introduced in the trough is by a piping system, and the piping system has smaller pipes that then they have an orifice plate here, which is different. The orifice diameter of the plate is different depending on the trough that is being fed. Because the central troughs need to get more liquid because they have more drip points. And so in order to achieve a homogeneous distribution, this orifice plate feeding every single trough has to be adapted. So first we checked how the liquid distributor is designed. We checked what is the liquid volume flow that the liquid distributor has been designed, and the operating range is the liquid volume flow that the customer is running the column is within the designed volume flow and operating range, or are we above or below? Then obviously a liquid distributor won't be able to work as good. But this was clarified. The problem was occurring under the design liquid volume flows for the liquid distributor. So the next thing is we rechecked all engineered parts regarding liquid distributor. Have we designed the orifice plates well? Is there any error in our calculation? Are the drip holes at the bottom of the troughs also correctly designed? And everything also regarding this issue was correct. The next question that we need to ask is, has the liquid distributor been correctly installed? As I said, the orifice plates are delivered, and they might have been interchanged. So the wrong liquid might be going inside, flow might be going inside a trough that shouldn't get that amount, or we need to check the levelness of the distributor, of the distribution trough. Obviously, this delivers a different height level in the trough, and then the liquid flow coming out will be different depending. So this is also something to be checked. Obviously, other problems could have been fouling, some forgotten issues, blocking part of or partially some of the troughs. This is an option that also could be happening, or others which we even don't know or cannot imagine. So what we did, we offered our customer to go on site and check the liquid distributor by ourselves. And we had the possibility to run it with water, open the column and go to the manhole and just operate it with water, and we could measure, we could see there was no debris, no fouling. We checked the orifice plates diameter, and mostly important, we checked, because it was running with liquid, we checked the liquid level height at every of these troughs building the liquid distributor, and the liquid level was it was homogeneous, so there was no reason, and the liquid distributor was leveled. So obviously both are depending on each other, but so there was we didn't identify any reason why on site why this liquid distributor should be causing the problem of heat not reaching the heat recovery and this temperature profile. So our eyes focus now on what was happening here on the lower bed, on the bed number 1, and mainly on the liquid distributor. So we looked at the drawing of the liquid distributor. This is something different, slightly different. On the one side, we have here these veins. The veins are again doing the function or delivering the liquid inside the troughs. The troughs, we have again a trough distributor, but we have the veins collecting the liquid coming from bed number 2, upper bed, here to the trough, so that the liquid that is going to be additionally be introduced mixes with the liquid above, and then it feeds the packed bed below. There is a piping system, but the piping system is not anymore directly feeding the troughs. The piping system is feeding 2 parting boxes or pre-distribution boxes. These are these things here, square, rectangular here and here. These are the parting boxes. Here you see a detail of the parting boxes, top side and side view here. Then the parting boxes, many of you know, they have openings on the sides, sometimes also on the bottom, but and from each of these openings feeds an individual trough below. So we needed now to check again. For this second distributor, for bed number 1, we needed to ask ourselves the same questions. We checked it was working within the design operating range. We checked all engineered parts, the slots in the parting boxes, the number of diameter that we designed, the 3 points, everything was checked. What we couldn't check, couldn't be made while we were on site, was the installation of the liquid distributor. And obviously all other questions related to seeing a liquid distributor. But what we needed to we could clarify is the orientation of the liquid distributor in respect to the temperature profile that had been acquired, and it was this orientation. So we will see now what the customer. We asked the customer if he had the possibility, please, to check. After we left, he had the possibility to check the levelness of the liquid distributor of bed number 1, and this is what they discovered. The liquid distributor was not well leveled. Better said, not the liquid distributor, but the supporting system of the liquid distributor. For such a big column, as you know, we need not only support ring, we need support beams. And they could identify that there was a difference in the level up to 20 millimeters from, for example, this side here and the opposite side. And these matched very well. Now you see the same picture, but we needed to rotate it in order to show the correct orientation in respect to the temperature picture that he delivered. And this is the liquid distributor orientation in respect to that. You can see that the minus 20 millimeter section, where the troughs are lower, where the liquid level on the trough will be higher, and therefore more liquid will come down here, is exactly located at this part, and where no liquid, because of this out of levelness, where much less liquid will be accumulating in the trough, will be this section here. So, and this was matching very, very well the temperature profile that they were measuring. And they repaired or modified the welding parts so that the levelness was just out of just a few millimeters, 1 or 2 millimeters, and after that the column reached the targeted heat recovery. So now we come to the next case study that we wanted to present to you. It has to do with a gas distribution problem. In this case, we are dealing with an hypochlorite absorber in a municipal water plant. So we delivered everything, not only the internals, but also the column itself, made of PVC ATFE. At the top, we are a solution of sodium hypochlorite is fed, and here at the bottom, a gas is chlorine gas is introduced. The distribution trace, the liquid distributor is consisting of ground holes, and the gas inlet device is consisting of a inlet pipe with ground holes for gas distribution. It is a small column with about 500 millimeters in diameter. What happened some months after start of operation of the column, the customer contacted us and saying that he was experiencing a chemical attack, probably a chemical attack occurring in the nozzle pipe L, which is just a level, it's just very near to the bottom of the column. It's just a nozzle to measure the level of the sump. And here you can see he holds a lamp here, a light, and it had been, the PVC had been so much thinner through corrosion, turned so much thinner that the light could be seen through it. And astonishingly, this was only happening at this very specific spot. He was not really experiencing any problem in the column, any problem in the goal of the column, but he was just having this problem, seeing chemical attack, and he contacted us. What might be happening here? We looked on every design data for the column, the gas load, the liquid load. We checked the gas velocities, the design of the pipe, gas velocity in the column, inside the pipe. We couldn't find really any failure in our design that could explain something related to here. It was difficult at the moment. At the moment, regarding data process data, not really yet much to identify. But then my colleague Uwe came to some idea, if just to explain why here locally, what can be here. So he thought that what might be happening is due to the very high irrigation density. We have 102 cubic meter per square meter an hour. This is a very high value. That the liquid, so much liquid carting just coming out freely out of the packed bed might be affecting the good, well-designed gas distributor in a way that some part of the fed chlorine gas is being pushed to this part and is therefore attacking or causing these problems with the chemical attack at that part. We not having much better assumptions for this problem. We discussed it with the customer, and we presented him the possible solution, or what we would like to try, or we would try to see if it solves the problem, was to separate the liquid and gas that they don't see each other. So how we do this, we use a collecting tray. Here you see the gas chimneys. The gas obviously needs to have path to flow up to the packed bed, but now the liquid will have to accumulate and it will be forced to come only through this central pipe, this downcomer pipe, and then flow out here in the sump. And the gas will come homogeneously distributed inside the column, then it will only flow through the homogeneously distributed chimneys here, and then it won't see the liquid and it won't be affected. And the fact is that we built this tray and the problem was solved. There was no further damage report after this modification was done. So again, a very successful story. So and now for the last topic regarding troubleshooting in droplets, regarding droplet separator, I will give the word to my colleague Uwe Franz, and he dealt with this problem directly, and he will present it to you.
Yes, hello. And this is a complete other thing, because it's now not on a column at land, it's on the scrubber on a ship on the oceans. And the problem was, you see the chimney of the ship, and you see a lot of droplets. And the droplets fall down on the ship and cause black spots. We call it black rain. This means that the inside mist eliminator in the scrubber was overloaded. So here you see the typical design of this scrubber. It's a spray scrubber. They're washing out SO2 with seawater, and the velocities are well on the limits of this system. As normally here, this is the exhaust gas from the motors, from the diesel engines, and here's a spray washing system, and on the top, a normal van type mist eliminator. And a van type mist eliminator has also, for the design, a maximum velocity when it works. And normally this maximum velocity is given to the active area of this van type mist eliminator on the net area. But we found this the engineering company who has done the design did this maximum velocity not of the net area, he took it on the gross area of the vessel. And therefore the mist eliminator got a very high a higher liquid, a higher gas load, like specified. And the customer asks us to find a solution. Another problem is, you understand, the ships should be shipped on the ocean, and the standstill times are very low, are very limited. And the scrubber was too small, and it would mean a very huge work if you have to done structural changes on the scrubber. It's an extremely high work. So we developed a very open pre-separator. Open means that the liquid load for this pre-separator could be very high. As it takes not out all the liquid, it takes out only a part of the liquid. And the other thing was the pre-separator should be simply suspended or hang up on the existing weld-in parts. This means the customer could make the modification in a very quick time. They had only to remove these existing blocks of the vent-type mist eliminator and hang up these new blocks inside. And here you see also a detail of this function. This was existing one, and this was a pre-vent-type mist eliminator, but we hang up also. The customer make a test on one ship. This was very successfully, and he also makes the solution in further ships. This was a very short example for mist eliminators.
Yes, and with that example, I think we have run on time, and therefore I would like just to summarize the presentation. I hope we could show you that troubleshooting is a rather complex topic that we need to develop very specific solutions to very specific problems. But we have accumulated a very a good experience throughout the last decades on troubleshooting. We have shown you further examples on how we develop different tower internals to solve troubleshooting problems. And what we would like to strengthen is that you please contact us at any time. We would be glad to listen to you and to discuss together on your challenges regarding troubleshooting and find together a solution, sharing our experience or learning together how to improve the plant and also our internals and products. Thank you very much. And if we are now open for any questions.